So let's look at two word problems that deal with linear inequalities. So this first one, we're looking at an elevator. It has a maximum capacity of 1,800 pounds. So that's going to be an important number, and let's just keep in mind that that's a maximum. If the elevator operator weighs 165 pounds, and each bag of cement weighs 80 pounds, how many bags of cement can be safely lifted on the elevator in one trip? Okay. So let's think about the weight that we're adding into the elevator. So we have this one elevator operator who's 165 pounds. So that's just a single weight. And you could think about, like, without any cement bags in there, we have this 165 pound weight. So that's the idea of a y-intercept. The idea that without anything else kind of happening, what's our starting number? So this is going to be our y-intercept. And then what's going to happen is the weight of that elevator is going to increase by 80 for each additional bag that we add on. So that's going to end up being our rate of change. For each bag, it increases by 80. So with that, that's describing our slope. So what we're going to do is have a variable x, which is going to represent the number of bags of cement. So that'll be our variable. And what we'll have is that we'll have 80 times x. The idea being that this kind of represents the weight of cement. So if we had one bag, it'd be 80 pounds. If we had two bags, 160 pounds. So you could see, plugging in different number of bags, we're increasing the weight. But then we also have our elevator operator, so we have this plus 165. So if I had one bag of cement, I'd have these 80 pounds of cement plus the elevator operator. So what we want to do is keep this weight below 1,800, or rather below and including 1,800. So this is the largest value we can have. That's our maximum. So what this will look like is this weight that we're adding into the elevator needs to be less than or equal to 1,800. We don't want it to go above 1,800. So 1,800 is going to be that maximum. So that sets it up. Now let's solve. So I'm going to subtract 165 from both sides. So that'll give me 80 times x is less than or equal to 1,635. X will be less than or equal to, if I divide by 80, sorry, I kind of skip that step there. And let's just go ahead and round this to two decimal places, so 20.44. So directly, what this is saying is that we need less than or equal to 20.44 bags of cement. And that would be an exact answer. That totally makes sense. You can answer it that way. The elevator can carry at most 20.44 bags of cement. And that's fine. If we wanted to get a little more realistic with it, we could do that. There's a few ways to think about it. We could assume that they're probably not, like cutting up these bags of cement, so that's where I'm a little hesitant to use the 0.44 in a more realistic sense, because to tell these guys, like, actually, I want 44% of one of those bags, they're not going to like that. So, or 0.44 pounds of, or 44% of that bag. So with that, what we could do is round. We'd want to round down, just because of rounding rules. Like the 4 would tell us to round down to 20. So what we could do is round this to a whole number, which would be 20. Something I would even think about is that if it was a larger number, let's say it was like 20.7, I would still want to round down, if that makes sense. Because if I round that up to 21, then we're adding weight on and the elevator might break, even though it's like a few little teeny tiny pounds. That might be enough for the elevator to break. So this might be a scenario where you'd always want to round down. But anyways, that's thinking way into it. It's an interesting discussion to have in terms of rounding, and we have our mathematical rounding rules, but sometimes we should be careful of applying those rounding rules because it might not actually work for the real world scenario. But anyway, I'm going to make a sentence with the value of 20, but you could use the 20.44 for exact. So I'm going to say the elevator can carry at most 20 bags of cement. So something that comes up with word problems with inequalities, like I could have said the elevator can carry less than or equal to 20 bags of cement, and that would be correct. This phrasing of at most says the same thing. It's telling me what the largest value could be. So there's some terminology that you can use that carries through that meaning of less than or equal to, more than. If we were dealing with more than or equal to, the phrase you see is at least. So if I said, okay, today I am going to eat more than or equal to 10 cookies. I'm going to eat 10 cookies or even more. That's my goal for today. I could phrase that as, today I'm going to eat at least 10 cookies. And that would bring the same idea across. I'm going to start at 10 cookies and then just go from there and see how many I can eat. Same thing with less than or equal to. If I said I'm going to eat less than or equal to 10 cookies, I'm setting a maximum. 10's the most, anything less is fine. But I could say it the same way of, I'm going to eat at most 10 cookies today. And it's kind of a limitation versus where at least it's a starting point. It's a minimum. Alright, one more example here. So a swimming pool is being filled with water from a garden hose at a rate of 10 gallons per minute. And this one, and if you see that word rate, they're telling, let's go with most of the time, they're telling you what the slope is, that rate of change. So we can see for each minute, gallons is increasing by 10. So you have this rate of change. If the pool already contains 70 gallons of water and can hold 230 gallons, after how long will the pool overflow? So the piece of information they tell us, so it already contains 70 gallons. So, get my highlighter. Yeah, 70 gallons. So that's our starting point. Without any extra water being added in from the garden hose, we're starting at 70. So that's our y-intercept. That's our starting point. And then they tell us a maximum. That's what this 230 is. It's this maximum capacity for the pool. So you can go up to 230. If we had 230 gallons in the pool, then it's completely full. But this idea of overflowing would be the idea of going over 230 gallons. So there's a few different ways you could think about setting this up, but let's go with the idea of, I want to see, for what times will the pool be overflowing? So setting up the equation for just how much water is in the pool, we have our slope. So there's 10 gallons per minute. I'm going to use, our variable, let me get our variable here, t, which is going to just be time in minutes. So time is passing. So we're getting 10 gallons of water for each minute. So in terms of how much is in the pool, if I had 1 minute pass, we have 10 gallons. If 2 minutes passes, I have 20 gallons, so on and so forth. So that's how our slope is going to work together with our variable. But we need to add on the 70 gallons that are already in there. So after 1 minute, I should have those 10 new gallons plus the 70 old, so a total of 80 gallons. And after 2 minutes, I have these 20 gallons that are just added in, plus the 70 that was already in there. So that's how our linear function is going to work. And then to see how long will the pool overflow, I want to see when is that amount of water in the pool going to be over 230. And I don't want to have the equals part there, because if it was equals, it wouldn't actually be overflowing. It would be perfectly full. So to look at overflowing, we're going to set it up with strictly more than. So I'm going to subtract 70 from both sides, which will leave me with 160. Then divide by 10, which will leave us with 16. So what this is telling me is for time, as soon as it passes the 16-minute mark, as soon as we go over that, the pool's overflowing. So the pool will overflow and then I'm going to use the word after, because it's like at 16 minutes, it's perfect, but then as soon as we pass 16 minutes, it's overflowing. Alright, so there are some applications of our linear inequalities.